All right, so now we're looking at total mechanical energy of a circular orbit. We'll also talk about how it gets extended for elliptical orbits. The elliptical orbit formula is the only one you'd expect to find on the formula sheet because it actually requires Kepler's laws to prove, and we're not actually going to prove Kepler's first law, which is the one we'd need proven to do this. By the way, the reason we don't do it is it takes like half an hour to an hour just to do that one proof, and I'm not asking you to do that on a test, so it's not worth our time. All right, but total mechanical energy of a circular orbit. It's going to be a similar situation to what we drew for the previous one. We've got an object. It is in a circular orbit around a much larger object, which means it will have some speed, it has some mass, our central body has some mass, and of course there is a distance r between their centers. We actually start off the same way by thinking about, oh wait, gravitational force is there. And that's going to be useful to us because the total mechanical energy is the kinetic energy plus the gravitational potential. And while we can figure out the gravitational potential pretty quickly at this point, negative integral from infinity to r of g central mass orbiting mass over r squared dr, integrate that through, get minus g mm 1 over r minus 1 over infinity, which just goes to 0. So we've got our gravitational potential energy. That's pretty easy. What we don't quite have yet is that kinetic energy. All right, so we're going to use gravitational force to figure that out. Basically, minus g mass of central body over mass, times mass of orbiting body over the distance between them squared will be equal to minus mv squared over r. This v squared over r with the minus sign, that's just the centripetal acceleration. If you're wondering why am I writing it minus, well, it's because I'm writing the gravitational force as minus to indicate it's towards the center of the large body. We can cancel stuff out again. And we just get that gm over r is equal to v squared. And in this case, that is all we want. We're going to substitute that in. So the energy will be 1/2 m big G mass of the central body over radius between the orbiting body and the central body minus big G mass of the central body times orbiting body over distance between. These look pretty similar. In fact, they almost are the same, except they don't quite have a common denominator yet. One has a 2 on the bottom, the other doesn't. So if we create a common denominator by multiplying by 1 on the potential energy side, now we can actually put them together. And you can see the negative term is bigger than the positive term. We get minus g mass central body, mass orbiting body over 2 times the distance between them. And that is the energy associated with being in a circular orbit. Cool. All right, what happens if it's not a circular orbit? Well, again, I'm not going to do a proof on this, but if we have an object that ends up following a trajectory that looks something like this, where it goes around in an elliptical orbit, we now have to think about the semi-major axis. So along here, this is the major axis. And it turns out the major axis is equal to 2a. And the value we need is actually a. So it turns out the energy will be related to the semi-major axis. And we'd find that the energy associated with an elliptical orbit would be equal to minus g mass of the central body, well, not quite central anymore, but the large body, times mass of the orbiting body divided by 2 times a, the semi-major axis. So pretty similar. And again, we're not going to do the proof for that. We actually would have to prove the equation and then do some work with it. I have done this before several years ago. And after spending basically an entire lecture doing proper Kepler's laws to prove all of this stuff, decided it's too much. So we're just going to worry about being able to prove the circular case. And if you can prove the circular case, just be aware that the r becomes a, the semi-major axis, if you're dealing with elliptical. All right, that is it for this little section. We're going to talk about period of a circular orbit next, and then we're going to try a problem.